So at this point, let's transition to the Q&A session. For any of the three speakers from this session, Clement, Sagar, and Nat. So Juven raised his hand.
Okay, thank you, Nat, and thank you. Wonderful talk. Question about this group extension. Can you just clarify again what do you have there? Just repeat what you say so I can ask the next question. There's a short exact sequence of group extension. Can you just rephrase again the condition? What do you have?
So I have a short exact sequence of the group extension.
You may
and
want
for
to
the charges. Oh, maybe I should do that. So the claim is just that the charge is mobile as long as this irrep can be pulled back from a non-trivial irrep of the quotient group. And otherwise it's fractonic. And in that case, it can actually pull back to a non-trivial irrep of the normal subgroup, which is the subsystem symmetry, which means that it's fractonic.
And I think in your example, both G and N are finite group.
G is a finite group and N is an abelian normal subgroup. Yes.
Right. But I wonder whether the finite group is necessary.
Yeah, for the lattice construction, we only consider finite group, but I think it's possible to go beyond to more general groups. For example, I think in your work that you considered U1, so probably
yes.
We have N is U1 here and G can be O2, for example. That's probably the example in your work.
Right. Yeah, maybe, yeah, thanks. I probably will think a bit and I'll ask again. Thank you.
All right, Rahul.
Okay, so for the conventional type 1 and type 2 fracton models, we have this nice way of thinking about the mobility constraints as coming from conservation laws on certain multiple moments of charge, or maybe combinations of multiple moments of charge. Is there an analogous way of thinking about these hybrid fracton orders, and particularly these non-abelian hybrid orders? And I guess this is either for Nat or Sagar, whichever of you prefers to take it.
Yeah, I'll say for the abelian orders, maybe in line with how we split up the talks. But for the abelian orders, yes. So for example, this hybrid toric code layer model that I showed. So in that example, if I were to view that as a gauge theory, it would be the condensation that I did to get that hybrid order basically broke the Z4 charge conservation symmetry in each layer. But it broke it down to a Z2 subgroup, which is preserved in each layer. So there's that planar constraint in each layer. However, there is still a Z4 global symmetry, which is preserved because of the condensation. So objects that are charged under the Z4 global, under the global symmetry, but not the planar symmetries or the mobile charges. And then if they're charged under the subsystem symmetry as well, they're immobile. So yes, that's, I think, a similar way of thinking about it. Maybe Nat can answer for the non-abelian case.
Yeah, it's sort of the same story for non-abelian, just that you have a global symmetry G. So for example, in the model, like the toric code, you have product of all vertex operators is 1. This is still the same for G. And that for N, this normal subgroup N, you also have a conservation law for each plane. And that gives you the restricted mobility for a certain excitation.
If I could just ask one follow-up, which is maybe also a little linked to what Juven was asking. So, again, for the sort of traditional fracton orders, one lesson has been that the consequences of the mobility constraints become much more dramatic if you move from discrete to continuous, Z2 to U1. Is there a reason why this cannot be done for the hybrid orders? If it can be done, then I would think that there's probably more to be found there.
Yeah, that's something we're thinking about. There's no obvious reason why it can't be, but yeah, that's definitely something we're still thinking about right now.
Thanks.
All right, other questions? Maybe I can ask one to Nat or Sagar. So when you listed out the models that you get from gauging different normal subgroups, you had 3 models, I think, for n equals z2 squared and z4, which all looked like they, just from listing the mobility constraints, they looked like they were the same models, just with some permutations on the charge labels. Is there a difference between those models, and more, and maybe also a little more generally, is there a principle for deciding which of these models are somehow the same phase, somehow akin to the foliation picture, where we're looking at equivalence up to decoupled layers of 2D?
Right. Let me share my screen again. So I guess there were different normal subgroups you could have chosen, but for example, the Z4 one is different from the Z2 squared because this sign rep and this sign rep are actually different because they have sort of different kernels. Whereas actually there are two possible Z2 square subgroups, and this turns out to be equivalent models because you can relabel these two charges. Yeah. So
Okay,
it turns out that these two are actually equivalent.
That makes sense, but physically, what's the difference between the Z4 and the Z2 squared one in terms of the set of excitations? Is it a difference in the fusion rules or in some braiding phase?
Yeah, I think it should differ in those. I mean, I haven't listed. This is just the pure charges and pure fluxes, so probably if you list out all of them, then they would be different.
Okay, and is there, do you have any speculation or thoughts on how we want to define distinct phases for these hybrid fracton orders? Do we want to use one of the more restricted definitions in terms of like the same sorts of definitions in topological orders where we just want to add local degrees of freedom and unitary circuits, or do we want to add decoupled layers of 2+1D topological order? Are we allowed to add in some other
I guess both is possible. At least for the abelian ones, we think that these are foliated. So the ones Sagar presented should be foliated in the sense that you can, for example, the one where it's hybrid between a 3D toric code and stacks of Z2 toric codes, you can peel off a Z2 toric code.
Okay, thank you. Media technology services.
Oh, hey, that's me. So I guess for the last two talks, you guys presented two constructions. One was kind of a condensation-based construction, right? And then the other was just by like gauging certain kinds of this sequential gauging process. So I guess so presumably the second construction works for the abelian examples too. But I was wondering whether in this non-abelian case you can do something like start with decoupled layers and you have a condensation procedure that works there as well.
Yeah, there is a one foliated model. I don't think Nat presented it, where in these one foliated examples, there's often a condensation based picture. And actually, I don't think in any of the three foliated models that we have, three foliated hybrid orders, that we have a very concrete condensation based picture. But the GN gauge theory construction that Nat discussed in generality is applicable to all of the examples. But maybe, yeah, Nat, maybe you can, since you talked about the non-abelian stuff, you can address maybe that S3 example.
Basically, the idea is you want to condense whatever stuff you want to make mobile. So by sort of choosing this choice of normal subgroup corresponds to choosing which excitations are mobile, and in the layer construction, you just condense pairs of those that you want to make mobile. But in the non-abelian, for the three foliated one, we don't have a G fracton order to begin with, so it's sort of, we don't know how to think of that picture yet because we don't have a model to start with to start condensing stuff.
Okay, thanks.
Ethan.
Yeah, hi. So do you guys know what the phase transitions look like when you do these kinds of condensation procedures? Maybe in the Z4 example that you were talking about?
Yeah, yeah, actually, maybe I can So let me just try to share my screen again. If I, 1 second. Yeah, the short answer to your question is that the short answer to your question basically is that certain transitions we are able to say that not only are they direct, but we're able to say what kinds of transitions they might be, but they're non-generic transitions in that I'm only allowing across that transition, many of the excitations are non-dynamical.
Right.
So in that case, sorry, let me share my screen. Yeah, so this is one of the phase diagrams that I showed. So if I start with this fractonic hybrid X cube order, which is an order in which the fracton excitations of the X cube model basically fuse into this mobile charge, which is E squared, which is like the charge in the Z2 topological order. So if I condense that charge, then you can actually drive a transition into this X cube order. And it turns out that along a special line where the only thing you're doing is condensing that charge, this transition is dual to just the condensation transition of a Z2 charge in a 3D topological order, which is somewhat intuitive. But away from that very special point, so where we know that the transition is not only direct, but it's a continuous transition, we can't really say anything else. For example, if I take the fractonic hybrid X cube model, we know that if you condense the line-on excitation, then eventually you should get to a 3D toric code order. But the nature of the transition, or whether it's direct, what happens in between is not known. This picture is actually the fact that the transition is direct. This is kind of generic. I think even for the Haas code model, there's a similar picture where there's a hybrid Haas code, and the transition is actually direct. I'm not sure if it's continuous.
But you said in the star in your figure is, I mean, don't you have to worry that like usually Higgs transitions in 3 dimensions are weakly like fluctuation driven first order, or
so let's see,
or is it maybe for Z2 it's different or something?
Yeah, so this yeah, let me check. I guess the right. So you're right. I think I always get I'm forgetting off the top of my head, but the one of the transitions is continuous and one is weakly first order. The one that's continuous is the one that's dual to the Ising transition in 3+1D. But so yeah, I think this might be, if this is the Higgs transition, which I'm just not remembering off the top of my head, then you're right that it would be weakly first order. But this is, we have a detailed discussion of this in our paper. I'm just not remembering.
Okay, yeah, I'll go check it out. And then if I can, just one more question was, is the ground state degeneracy in these theories always like, I can just take the fracton part and the deconfined gauge theory part and like multiply the ground state degeneracies, or?
Not for, at least definitely not for this one foliated example I showed. For example, there's some subleading correction. It's not, the ground state degeneracy is not trivially the, I don't think it's, but for some of these other models, I think it is.
For the abelians it is, but for the non-abelians, probably not.
Yeah.
I see, okay. Thanks.
All right, Julian.
Thanks. Sorry, just to clarify again, and also to Nat and Sagar. So if I use the extension, groove extension way of thinking that Nat just mentioned, and to apply to what the Sagar talked about, this Z4 condensed Z2, this model, is that the G is Z4 and N is Z2?
Yes.
So that approach works. But I want to make sure, because you choose the N as some abelian normal subgroup, but you interpret this as some subsystem symmetry. I was wondering how this data is specified. The question I want to ask further is that, can you replace this by some maybe vector or higher polynomial type of global symmetries? And that's the way I kind of relate to what I have. And maybe you already mentioned, but I just want to make sure, because it seems like you write some N, but how is the subsystem the data of subsystem symmetry encode layer in the slide.
I mean, there's some geometric dependence. So
Right.
so G comma N itself, if you ignore the geometry, you can treat it as a group. But of course, for fractons, we want to specify some the geometric dependence as well. Sorry, I'm not sure what.
Yes, but then what are the constraints or some consistency data? What are the constraints written in the extension there? There should be some constraint, right? For example,
well, at the group level, at the group level, it's just the usual group extension. But I guess you mean how the symmetry acts on, say, lattice model.
Yes. Yeah, there could be different.
Yeah, then there are probably some twisted transformations. Maybe it should. I guess an analogy would be sort of similar, like to a two group where you sort of extend a one form by a zero form, and then you have some sort of twisted gauge transformation. So there should be a similar one in this case as well.
Okay, so I assume there are some data not specified fully from what you write. You need to specify a bit more about the
geometric data as well.
Yeah, that's right. That's what I think. Okay, great. And I suppose I can replace this n to the vectorial polynomial global symmetry of some u1 product of u1 with the spatial vectorial higher order dependence, and that will relate to what I had, I think. All right.
Yeah.
Thank you very much.
So.
Thank you.
I guess
Right.
to add to that, I'll also.
Sorry.
Yeah, sorry. To add to that, I'll also say it's not just the geometric dependence of the geometry of the subsystems, but implicit in I think implicit in our construction for both the one foliated and three foliated GN gauge theories, what we're saying is that if you take an appropriate product of the subsystem symmetries, you get a global symmetry, and that global symmetry is a subgroup of the full global symmetry of the system. And so for more complicated geometries of the subsystem symmetries, maybe that's also some degree of freedom that needs to be specified, I guess. So it's not just the geometry of the subsystem symmetries, it's how they're kind of embedded into this global symmetry. So.
Okay, thank you.
We still have a few minutes if there are still some questions for the speakers. All right, if not, in that case, we can take a break for about 8 minutes, it looks like we have, before the next session starts at 12:15. Thanks again to all the speakers from this session.